so I think we can start. Welcome after the break in a second part of our minor solar system body day. And now the talk will be given by Tomasz Kwiatkowski, who will tell us about the physical characterization of near-Earth asteroids. So, Tomasz, please, the stage is yours.
Thank you, Edyta. Welcome, everybody. I'm Tomasz Kwiatkowski from Adam Mickiewicz University in Poznań, Poland, and I would like to tell you about a special type of observing campaigns that are targeted against the very small near-Earth asteroids. When I write proposals for observations of those small objects, I usually deal with time allocation committees in which there are plenty of people studying stars and galaxies. So I have to persuade them that to observe such small pieces of rocks is important. Usually I provide them with the following arguments. First, near-Earth asteroids could be the source of water on Earth, so they may be important for the evolution of life on our planet. Second, because of potential collisions with the Earth, they may pose a danger to humanity, so we have to know not only their orbits, but also what they are made of. Third, those asteroids can be used as sources of raw materials for the industry, and as they come close to Earth, they can be easily get in terms of delta V with the energy used for the spacecraft. So they are easily accessible by space missions. And fourth, the smallest of asteroids are subject to non-gravitational forces like the Yarkovsky and YORP effects, and those two effects are important for the evolution of our planetary system, but also for the evolution of debris disks around other stars. Especially this last argument is convincing for those galaxy and stellar people. So let me tell you about this kind of campaigns. I call them fast and bright because during close encounters, like what I mean close is several lunar distances. During those close encounters, near-Earth asteroids are bright because they are so close. Even if they are small, by small I mean 100 meters or even 10 meters, even they are small, they are bright and can be observed with small telescopes. And during such close approaches, they quite often sweep a long arc on the sky, so they are observed with from different geometries. And this helps to get their spin axis and shapes just from one passage, from one apparition. So imagine during 2 weeks, you can collect enough data to get a shape model of those objects. What are the drawbacks? What are the difficulties of observations? Big sky motion. As they are close, their sky motion is high, and quite often they need non-serial guiding, so that on your images, when you track on the asteroid, the whole light of the asteroid falls within one circular point spread function, and the stars are elongated. We can deal with such images. We can do differential photometry. You can calibrate them, but you need this non-serial guiding. And second drawback, short observing window. Imagine that the new object is discovered, and you have to respond within several days. So how to collect all those observers, how to build a network, ad hoc network, to collect data on those fast-moving objects. This is a challenge. Uh, Among those near-Earth asteroids, there is a special class of objects which are called very small asteroids. Their diameters are smaller than 150 meters, and they are thought of as monolithic boulders, building blocks of larger asteroids. The larger asteroids, several kilometers or tens of kilometers in size, are thought of as mm, rubble piles composed of smaller boulders, And those boulders are very small asteroids. And because of their small sizes, many of very small asteroids show very fast rotation. So they are called super fast rotators. By fast rotation, I mean periods as short as tens of minutes, even. So to observe them, you don't have to spend many hours during the night. If you collect enough photons, half an hour can sometimes be enough. And because of the small sizes of those very small asteroids, they are best observable as near asteroids because they are also in the main belt, but we don't see them because they are so small. And they respond to non-gravitational YORP effect. So studying those very small asteroids within the near Earth asteroid population is a laboratory for studying the YORP effect. And most long arc near us asteroids are very small asteroids. So now I will focus on very small asteroids only here. I will talk about near Earth asteroids, thinking about those smallest objects. Uh, I would like to show you four observing campaigns of those long arc very small asteroids that will maybe illuminate the details and difficulties of such campaigns. First campaign, we launched it in February 2015 for 2015 AZ43. In that campaign, 7 telescopes participated with diameters from 0.7 meter to 4.3 meter. One amateur astronomer also observed this object, but independently, not knowing about our efforts, so it's hardly to call him a collaborator at that moment. With the data that we collected, we were able to derive the spin axis and shape of this object, but the result was ambiguous. So no paper was presented as a result. We only showed a poster, which you can see at the ADS BIP code. And this object swept an arc of 122 degrees in the sky. And I talked to Josef Durek about how long the arc should be to get this shape model. And he thought for a moment and said, well, it's about 120 degrees. So you see that this rule of thumb was fulfilled in this case. And for this 70-meter object, we collected enough data for modeling. And the rotation period was 36 minutes. And the apparent magnitude during observations was from 17.2 to 19.6. So you can see that it was accessible even to smaller telescopes, 17.2. Another campaign we conducted a year ago in March 2021. In this campaign, uh, already 10 telescopes took part, and the telescopes from 0.28 meter, that was Tomasz Kwiatkowski, who is listening probably to my talk now, to something like 1.2 meter Calar-Alto telescope. So a range of diameters, and also four amateur astronomers joined in. How did they know about the campaign? Through the Minor Planet mailing list, because that's the list which is read by many astronomy researchers. And with the data that we collected, we were able again to derive the spin axis and shape. This time we had only two solutions for the spin axis, which is typical. We also got the taxonomy of this object and a phase curve. And the arc was 130 degrees in this case. The object was smaller than previously, 30 meter only in diameter. And just look at the rotation period, 50 seconds. This meant that we had to expose for 5 seconds, not to dump higher frequencies, higher Fourier frequencies in the light curve. But the apparent magnitude of the object was from 14.4, which means it was accessible again to small telescopes. And even if you couldn't get a sufficient signal to noise ratio on one image, if you collected lots of images, like Tomek Kluwak, I guess he collected 2,000 images, and he combined them, averaged them, and he managed to get a decent light curve out of it. So by proper observing strategy, you can observe such fast rotating objects even with quite small telescopes. And results were published in Astronomy and Astrophysics last year. Another campaign, 2022 AB, it was finished like 2 or 3 weeks ago because it was in January this year. This time, 26 telescopes participated. So we can see there is an increase from 7 through 10 to 26 telescopes nowadays. So we are kind of expanding. And again, the diameters were from 0.28 meter to this time it was 10 meter SALT telescope, which was used at the end of the track. In the campaign, 8 amateur astronomers participated. Again, you can see an increase from 1 amateur astronomer through 4 amateur astronomers, and nowadays 8 amateur astronomers. And they provided real useful data. What was quite interesting about this object was the unique phase curve, because the minimum solar phase angle was 0.3 degrees, which is uncommon among near-Earth objects. So we hope we'll be able to get the opposition effect well sampled. I say we hope because the data are still in the process of analyzing. And the last, and I must say about the arc. The arc is 103 degrees. This is because I had to decide when to put the last light curve on the path. And this was this SALT 10-meter telescope. I had half an hour of target of opportunity there and should decide which night the observation should be done. And the weather was going worse. So I said better get, if the weather is clear, then risk that nothing will be done 2 or 3 days later. So I cut the arc from 120 to 103 degrees. We will see what we can get from this shorter arc if we'll get the unique spin axis. And the diameter of this object is bigger, it's 100 meters, but the rotation period is again quite short. It's about 3 minutes. And the apparent magnitudes during the observations were from 16.3 upwards. So again, it was accessible to small telescopes. And so the smallest telescope used was 0.28 meters, a meter class instrument. Okay, and the last campaign is the campaign that never happened. Actually, the object is now observable. We planned for that long before because my PhD student Paweł Koleńczuk, who is presenting a poster at this conference, got the light curve of this object last year. He determined the rotation period of 55 seconds, which is a fast rotator. And so we planned to observe it this year again when the arc will be 130 degrees. But there is a difficulty. This is caused by the apparent magnitude, which is less than 18. This means that to cover the substantial part of the path on the sky, we would have to use big telescopes. By big, I mean 2-meter plus. And this is not so easy to get. So since 2022 AB appeared just before, you see, January 2022, we did this campaign, and campaign planned for February 2022. We decided to quit this campaign, so it was never started. So you can see that such objects I'm talking about fly by the Earth from time to time, that such observations can be done, and all is needed is a fast response with telescopes. So the best observers are those who are at the telescope when the object is discovered. And I must say that I realized that I I used the Europlanet network of telescopes that we are talking about here for this 2022 AB campaign, because Christian Sarnecki wrote to me, the guy from Hungary, that they also observed this object, having heard about the campaign on the Minor Planet mailing list. So they will provide us with the data on this object, being collaborators. So not knowing, we used the Europlanet network as well. So now about the lessons learned from this all those campaigns. First is that when you observe on short notice, it is very difficult to coordinate observations. So duplication of efforts is inevitable. The weather is a problem. Sometimes people the second thing is collaborators not always know how to observe fast-moving, rapidly rotating NEAs. They join the campaign because they have telescope time and the night is clear. They want to observe. They have a good instruments, but they don't know how to do it, and it's not that easy to instruct them during the campaign because there are so many telescopes participating. So sometimes they make their own decisions which are not optimal, not to say wrong, especially when there is a moon in the sky and they have to observe 30 degrees from the full moon and the object is like magnitude 17. Then the filter is important, the exposure time is important, so all those details sometimes they are not optimal. Next, some observers show up only after the end of the campaign. In the campaign this last year with the campaign of 2022 AB, we had such cases. I heard about some observations being done from Pic du Midi, and but the results I got only after the campaign ended. So fortunately, the observers were well experienced in those kind of observations, and we got very good data from this almost 3 kilometer at height observatory when the object was passing the full moon. So they observed like 20 degrees from full moon. But because of the height of the observatory, we got good data. So other obstacles in observations, bad weather, I already mentioned that. So uh, sometimes you cannot coordinate, you cannot plan well. The moon, uh, and the Milky Way. So the Milky Way, I remember that for the first the campaign last year for 2021 DW1, the object was first on the Milky Way, close shortly after its discovery. So there was a question when to start. I was too conservative maybe, and Brian Ski from Lower Observatory was more adventurous, and he started to observe when the object was jumping from one star to another. But throwing away, I guess he said 30% of frames were not usable, but using the rest of the frames, he managed to get the rotation period of 50 seconds, which helped to plan next observations. So Milky Way is an obstacle too, and we have to know how to deal with it. And to end my talk, I guess I don't have much time, just to show you briefly a few slides about the results of one of the campaign, DW1. There is a path in the sky that the object swept. There is the distribution of the positions where light curves were obtained. So you can see the cover is more or less good. There is a selection of the light curves obtained. Some are very noisy, but many points make the Fourier fit quite reasonable. There is a model, two models actually, for two spin axes derived for this asteroid. There was a taxonomy derived as well from color indices obtained during observations. So it was an SQ class from which the average albedo could be determined. We observed only also the phase curve, but not small phase angles. So the H value was rather not very accurate. And that's all what I want to tell you. Thank you very much for your attention.
Thank you, Tomasz, for this extremely interesting talk showing another possibility how the amateur observers can join and help in observations, very demanding one in your case. So now we've got time for one or two questions.
Yes, Thomas. Congratulations for your presentation. It's very interesting. How could we be aware of a campaign? Do you have a website where you announced a campaign and the object you have selected for a survey?
Well, the best way would be to subscribe to the Minor Planet mailing list. It is read by more than 1,000 asteroid researchers, and you can learn from it about different campaigns. Unfortunately, not many people announce their campaigns there. Just they choose to keep them to themselves. But that's the best place, because we tried to develop different services for that. Believe me, and we made people aware that there are websites, there are like even web forms to announce campaigns, but it never worked in practice. So the mailing list, where you receive emails, proves to be the best. So please subscribe to Minor Planet mailing list.
Okay. Okay, and are you scheduling also, I don't know, a training session to enroll the amateur to get them ready for a real campaign?
That's a very good suggestion. I didn't think about it, but you may be right. Thank you for this, because really, I had some people participating in this January in the campaign, and they were not familiar with those fast moving targets. So I spent some time explaining by email to them the details, and sometimes I sent 3 or 4 emails to 3 or 4 persons. But what you suggest would be helpful. Thank you. I will think about it.
Yes, for sure. Such some kind of tutorial for observers who wanted to observing would be really helpful. That was also my comment after your talk. And I think we've got one more question from John Davis.
Yeah, thanks very much. Yeah, I recognize your problem about scheduling at short notice. Just at the risk of repeating what I've said yesterday and the day before, that this Opticon RadioNet Pilot Transnational Access Program offers a single proposal to a range of telescopes. And we do time critical and triggered observations. So in many respects, what you're talking about is no different to a supernova. You can't be sure when it's going to happen, but you know it's probably going to happen. And you could start with start with a small telescope and then transition to a bigger one as the asteroid gets fainter. That's exactly what the supernova people do. They ask for observations from a small telescope when it's bright, and then as it fades, they ask for observations a week or a month later with bigger telescopes. So I think offline, maybe it might be worth talking and seeing whether we can construct a way of making proposals like this to our network, because our network is 1.5 to 11 meter telescopes and includes SALT, by the way. And I'm an asteroid astronomer, or at least I used to be, so I understand your problems. So if you want to have a chat, offline next week, remember we've got a call open right now that's open until the end of February. So I just wanted to flag that as a possibility for anyone who wants to do these kind of coordinated observations, because you only have to pass one tack. You don't have to get time on 10 different telescopes through 10 different tacks.
Okay. Yeah.
Okay. So thanks for giving me time for that little advert there. I'll turn myself off.
Thanks for the suggestion. Yeah. Thanks for the suggestion, John. Thank you. I will contact you about that.
Yeah, and we've got one more question on chat. How well constrained are these rotation periods? It must be quite challenging if your exposure times are similar or greater than the rotation period.
Oh, yes. That's a good question. Not knowing the rotation period in advance, we have the strategy of doing spending part of the time with the 5-second exposures and the other part of the time with 30-second of exposures. So each part we try to keep, like the first part 1 hour and the second part 2 hours. In this way, we are able to detect anything from 25 seconds rotation period, the shortest, up to 2 hours or even more, because sometimes if you observe half the light curve, you can estimate the rotation period to be twice as long. So yes, not knowing, we have to use different exposure times. And the rule of thumb actually proposed by Petr Pravec from Ondřejov Observatory is that if you want to sample well the second harmonic of the light curve, you should expose with 0.18 times the rotation period. So if you have rotation period like 25 seconds, the shortest, the longest time is 5 seconds to detect the second Fourier harmonic with good signal to noise ratio. Doesn't mean that the light curve shape will be okay. It may be damped, the amplitude may be made smaller, but you will detect the rotation period. So about 20% of the rotation period should be your longest exposure time.